Okay, thank you very much. I'm very glad to be here. It's a very tough spot after such an amazing presentation, even with a song. I don't have one prepared, I'm sorry, but I hope it'll be interesting anyway. So I'm not going to talk about healthcare either, sorry. I'm going to talk about science and maybe engineering, if you count materials into the engineering bucket. I'm from Microsoft Research AI4Science. I'm based in Berlin. And yeah, I'm going to talk about our generative model on AI, but first I want to spend the first couple of moments to talk about the bigger picture of what we're doing at Microsoft. So materials design, so coming up with new materials, is one of the biggest cornerstones of modern technology. If people talk about we want to solve certain sustainability or climate change problems with technology, a lot of the times materials could actually be the missing piece that help us address those problems. For example, carbon capture, better batteries, solar cells, you name it. The problem though is that materials design is incredibly lengthy and expensive process. So it can take 20 years or longer from maybe, let's say, a first proof of concept to having a material that's actually usable in practice. And of course, that we don't have a lot of years left if we want to address pressing issues. So our goal is to accelerate this process dramatically with the help of AI. The central question that we're facing in materials design is how can we find a certain material that satisfies all the constraints or all the properties that we needed to have for use in practice. Of course, for example, for a solar cell, it should be able to produce electricity very well, but also the materials have to be useful in practice, so they should be usable for over a long time, they shouldn't degrade too fast, and there are many other potential additional requirements, and satisfying all of them, and many of those requirements even contradicting or conflicting, is really, really challenging. What do we do at Microsoft? So we kind of see this cycle, or like this workflow in materials discovery, where you have a material candidate, let's say a generative model, or even traditional models. They come up with something that might be useful for a certain application, but then you don't know, A, whether you can make it. That's the first important problem. And B, you also don't know whether it fulfills all the properties that you have in mind. So you need tools to measure the properties of the candidate that you have in mind. And usually those will be computational, because making something is extremely expensive and difficult. So you don't want to take any random candidate that you may come across and give it to an experimentalist. They will be very annoyed with you if you try to do that. So we need good computational tools that can tell us the properties of a potential candidate. The problem though is that even the best computational tools we have are very expensive sometimes to compute material properties. So, if it takes days on multi-CPU machines just for a single material candidate, you cannot take hundreds of thousands of them to find the very best one with the properties you have in mind. So, what do? So we develop generative AI to come up with new candidates that hopefully can be made and fulfill the properties that we have in mind. But then also we have a work stream that's on AI emulators. So these are models that are very good at computing the material properties of the candidate you have, so that we can rapidly cycle through candidates much faster than you could ever if you were to go through the experimental route, or even with standard computational tools based on density functional theory. I'm only going to talk about the generative AI part, but we also have a paper that recently came out on the emulation, and you're very welcome to give that a read. It's called MatterGen. All right, but today it's going to be about the MatterGen part, the generative model for inorganic materials design. So what's the traditional workflow if you want to find a new candidate material for your problem? Maybe you want to capture some carbon. usually you start with some database. So people have constructed databases of existing, sometimes even also only hypothetical materials that nobody has ever made, but those are like postulated that maybe you could make it, but we don't know what properties they have maybe. And then you take either the, maybe somebody has already computed the properties that you're interested in, maybe you have to do it yourself, but in any case, what you're going to do is you're going to take the properties that you have in mind, and you're going to just filter them down. You're going to start with maybe 10 to 100,000, and you just apply filter after filter, after you're only left with maybe order of 10 that you can manually look through, maybe show to an experimentalist, and they will tell you, oh, the first 5 maybe I can make, but the latter 5, no way of ever making them. Then you'll try to make the first 5. That's how it usually works. And the problem, of course, is if the thing you're looking for is not in the candidate set that's already existing, then you have no hope of finding the thing you're looking for. Recently, there was a paper by Google DeepMind where where their approach is basically to increase this input set for this funneling process. They came up with a data set that expands the material space computationally by about 10x. And also there has been a recent effort by colleagues at Microsoft, so not my team, different department, but still at Microsoft Azure Quantum, where they speed up this whole process from database to candidate you actually make by 1,000 times. So something that they said that usually takes decades, they did in months. So that was very impressive. And in our generative workstream, we believe that the next frontier is to just vastly expand the known set of materials. So the problem is we have maybe order of 10 to the 6 known materials, and most of them haven't been made yet. Most of them are just hypothetical and just computational, basically. But the design space of novel materials is enormous, maybe 10 to the 10 or 10 to the 12. So we really want to tap into that set of materials that nobody's ever come up with before, because there's probably going to be very, very useful materials in that set that we haven't tapped into. So this is where our model comes into play. So we train on existing data of stable or predicted to be stable materials, and we train a model that can do property-guided design. So you tell it some property value that you have in mind, and the model will do its best to come up with a candidate that hopefully fulfills that set of properties. So let's go into a bit more detail. So what do I mean when I say a material? So that's also something I had to learn. So my background is not material science, I'm a computer scientist, so I had to learn this when I came into the team. So crystalline materials are solids where the atoms form a periodic arrangement. And what do I mean by that is you have some unit cell that is defined by these 3 lattice vectors that span the unit cell, and inside the unit cell you have some number of atoms that are inside the unit cell. They have some atom types, so of course they can be carbon, hydrogen, lithium, you know it, anything from the periodic table. And they have some coordinates inside the unit cell, of course. They need some 3D coordinate. Now the interesting thing in materials is that the assumption is that in this crystal, this unit cell repeats infinitely in all 3 spatial dimensions. And that has some interesting consequences. For example, if, let's say, you simulate a material, so you simulate atom movements, and one atom gets kicked out of the unit cell because of some force, this periodicity implies that what will happen is that it just enters the unit cell from the other side again. So basically the mathematical term for this would be that we're dealing with a hypertorus. So, and that has some interesting consequences when you're trying to design a generative model that we'll see in just a moment. Right, but keep in mind that we have these three components of the data. So the atom types that are discrete. We have the atom coordinates that tell us where inside the unit cell the atoms are placed. And we have these 3 lattice vectors that tell us the size and the shape of the unit cell that repeats infinitely in all 3 space dimensions. what does it mean that when I say we're learning a generative model for materials? Really, we're trying to learn a model that comes up with plausible combinations of atom types, atom coordinates, and lattice matrices that, taken together, form one material candidate. And the learning objective is that we hopefully will be able to generate any metastable. So stable means it's really the lowest energy structure that you can have in that chemical system. And metastable means it's maybe not the lowest energy, but there's still hope that you can make it. So there's some cutoffs, some thresholds that experimentalists have come up with where even though you may be not the most stable structure in the chemical system, with certain tools in synthesis, you may still be able to synthesize them. For example, diamond is an example. It's quite far off what we call the convex hull, so it's not the lowest energy phase of carbon. For example, graphite has much more lower energy, but with certain conditions, very high pressure and so on, you can still make diamond and it will be stable even at room temperature. And then what are the desiderata? So we want to have a generation process that respects the properties of 3D materials. For example, it shouldn't matter how you rotate globally a material. It's still going to be the same. It's going to have the same energy. It's just arbitrary how you define the rotation and so on. We want to handle the periodicity appropriately. So the thing that we just talked about, if you move an atom outside of the unit cell, it'll just re-enter from the other side. And we want to be able to add property conditions. So just coming up with completely random proposals is probably not the most useful, because then you still have to look through millions maybe to find one very specific material that you may be interested in. But instead, we want to guide the generation process with some property constraint in mind, so that we only have to produce maybe 1,000 or a couple of thousand that are hopefully very targeted around that property value that we have in mind. The architecture that we use for our model is that of a diffusion model. You may have heard of it. So it's easier to explain it looking at images. So we start, so the training process is that we have a data set of images that we call X0, and then we just gradually add more and more Gaussian noise to the images until at the very end, the images just come from a standard Gaussian distribution, for example. And then the task of the model is really to learn to invert this corruption process by basically by undoing the noise that you add to the picture, to the image, so that finally, when you're done training, you can just start with a completely random sample and gradually refine it so that you hopefully have a realistic and nice-looking image in the end. What does this mean for materials? It looks a bit different. So remember, we have these three components: the atom types A, the atom coordinates X, and the lattice vectors L. And we're going to corrupt each of those independently, given the input material. So we're training on the material from a database that we think is high quality, and then we're gradually adding noise to it, and I'll go into a bit more detail what that means for all the three components of the material. But in the end, we hope to be, in the end, we know that the materials at the end of the diffusion process, they come from some distribution that's completely random, that has no information left about the input data point, so that finally, when we want to sample, we can just sample from this random distribution and reverse the process. So we define this forward process Q that, given some intermediate material, so A t minus 1, X t minus 1, and L t minus 1, so that's some intermediate noisy material, it just defines the distribution of the next slightly noisier one. And I'm going to tell you what distributions we chose for each of those. We make this assumption that given the input data point, these three corruption processes, they factorize. So they don't know about any of the other corruption processes. So basically, given your input material, you can just diffuse the atom types, the atom coordinates, and the lattice independently. But of course, because the reverse process doesn't factorize in the same way. So in the reverse, you still have to take into account the full material if you want to compute the probability distribution for the denoised one. Now let's see what we do for each of those three diffusion processes: the atom types, the coordinates, and the lattice. For the atom type diffusion, we leverage a method that was published at NeurIPS 2021. It's called D3PM, and that's really basically a generalization of the original DDPM, which is called denoising diffusion probabilistic models, to discrete types, where you can't just add Gaussian noise, because your atom types, whether you have carbon or hydrogen, you can't add Gaussian noise really to a discrete quantity. So the key idea is that they define some Markov transition matrix Q that basically just corrupts and basically gives you the probability of transitioning from your current atom type to another one. For example, you could just swap the type carbon with hydrogen, so that in the end maybe all the atom types are uniformly distributed, and that of course is a distribution that we can easily sample from. The particular instantiation that we use is slightly different. So we use what they call the absorbing or masked diffusion, where at any time step you just have some small chance for each atom that it'll transit into a masked state. So it's a non-physical state. It's not a known atom type. It's just something else, a masked or absorbing state. And once it's there, it'll stay there until the rest of the diffusion process. So really, basically, if you look at the diffusion process, you'll have the input atom types that are maybe carbon, hydrogen, and then gradually you'll see these gray atom types. These are just the masked atoms. So just over time, one after another, they'll be masked. They'll transit into this masked state, so that in the end, you only have these gray atoms that have no more information about the type that they came from. And then you really want to, given the information that's still encoded in the atom types, here at this noisy state, the model can maybe infer what will be the atom types of these masked ones, and it'll try to predict that. For the fractional coordinate diffusion, so the coordinates inside the unit cell, this periodicity that I mentioned, this implies that we can't just take a standard diffusion process where we just add Gaussian noise and we're done, but we have to be a bit more clever, and we basically we use some methodology that they've come up with at NeurIPS 2022, where they talk about angles, torsional angles in molecules, and really the principle is the same. So we're using a wrapped normal distribution, so it's just a distribution where you can think about it as a normal distribution that's maybe defined on a circle. So you just wrap around whenever you hit the boundary, and that means that if you just add more and more noise, so your sigma in the Gaussian increases, finally you'll just end up with the uniform distribution that is also easy to sample from, of course. Now, what's the problem with that? If you want to express the likelihood of a noisy sample given your input, for a Gaussian, that's very, very easy. Of course, we know the closed form expression, but for the wrapped normal, we have this nasty infinite sum over all the integers that basically, intuitively, you can think about it how often you have wrapped around your data space, and of course, since the Gaussian has infinite support, you could have sampled something that has wrapped around very, very often. Of course, it's very, very unlikely, and that's also in the end what saves us, because the thin Gaussian tails enable us to just approximate this infinite sum with a truncated sum, and basically at no cost in accuracy because of the exponential decay. Right. Now, what do we do for the three lattice vectors that define the unit cell, the shape and the size of the unit cell? So one first obvious problem is that if you take three-dimensional vectors, well, you have 9 numbers, so you have 9 degrees of freedom, but actually the lattice matrix of a material only has 6 degrees of freedom. So you can represent it completely with just the 3 lengths of the lattice vectors plus the 3 angles between the lattice vectors. And that's your full description. There's nothing more to add. But all of a sudden now we have 9. Where does that come from? The answer is that you have in this in these 3 by 3 lattice matrix, you have the rotation degrees of freedoms also in there. So you could have arbitrarily rotated the lattice, and that wouldn't change the lengths or the angles between the lattice vectors. So if we want to use the 3 by 3 representation of our lattice vectors, which is very convenient to work with, then we have to do something to get rid of these 3 extra degrees of freedoms. And the solution that we went with is the polar decomposition. It's based on the singular value decomposition. It's quite well known, and you just basically what you get out is you feed any arbitrarily rotated lattice matrix into it, and what you get out is a symmetric matrix where all the off-diagonal entries are symmetric, plus a rotation matrix that we just throw away because we don't care about the rotation. But this gives us, for example, if you get some data point and it could be arbitrarily rotated because whoever gave it to you is completely free to choose how they rotate the lattice matrix, we can basically undo that rotation and have all the lattice matrices that we train on basically rotated in exactly the same way. We have another twist on the lattice diffusion because with very early experiments, so the first naive thing that you're going to do is probably use the vanilla DDPM, the most widely used diffusion model corruption process that just ends up with all your entries in the lattice matrix coming from a standard Gaussian. The problem with that is you'll end up with extremely skewed and very, very small lattice matrices that are completely unphysical. So if you want to have, so basically if you look at the volume, it'll be extremely small. So maybe orders of magnitude below the volumes that you find in your training data. Now if you want to have one single denoising model that takes you from so in principle it's not a problem, of course, you can just denoise it, but if you just want to use one model, which we typically do in diffusion models, that takes you from the very noisy state to the clean state, basically, with the data, then this model would have to operate on volumes that are across many different orders of magnitude. And that's very challenging because fundamentally we use a GNN that's based on distances, distances between the atoms. But now if you have distances that are maybe 0.001 angstrom and 5 angstrom, then the model is going to have a very hard time generalizing across these orders of magnitudes. So what we do instead is quite simple solution. It's just we add to the mean, instead of having a 0 mean, we just have a mean that on the lattice matrix has some finite positive mean on the diagonal elements. That means that the mean of our noise distribution is just the cube, and then you just add some noise to the cube with certain volume, and that just that fixes the problem and empirically works a lot better. So the first one basically didn't work at all, and then the one on the right is the one that we actually use in the paper that works really well. Now, we can throw this all together and try to come up with, now that we have the forward corruption processes in place, now we can try to think about how we can come up with the reverse. So a parametric model, a neural network that takes in some noisy material and predicts the distribution over a slightly less noisy material. For this, we use what we call an equivariant score network. I'm going to tell you what that means, and that's based on a graph neural network where, you take the input material and you're building edges based on how close atoms are, and that defines your graph, and then you can have message passing on that neighbor graph. That's fundamentally how it works. Now, what do I mean with equivariant? So the one important property is that if you that the model we have, if the input rotates, the output rotates in exactly the same way. This is really all that equivariant means, and that reflects the fact that it doesn't really matter how you rotate your input, the model shouldn't care. So by enforcing that the model output rotates with the input, we kind of the model cannot predict something completely different for a slightly rotated material, which wouldn't make any sense. That's true for the coordinates and for the lattice. So they rotate, but the atom types, of course, they are what we call invariant. So here the model just produces the exact same prediction no matter how you rotate. The model, of course, for the atom types, they're not a geometric quantity like maybe the coordinates or the lattice. They're just discrete types, so it really doesn't matter for the model how you rotate your input. It'll just produce the same prediction for the atom types. And then with score model or score network, I mean that we have a model that approximates the gradient with respect to the input of the log likelihood of our noise process. So our noise process takes in a clean data point X, or M if you want to call it a material. It'll give you a distribution over noisy states, and what we want to approximate with our model is the gradient of that likelihood with respect to the input. And that's why we call it a score network. That's really all there is to it. The backbone architecture that we use is GemNet. It's widely used GNN that's used for all kinds of molecular property, or like molecular tasks, like simulation, property prediction, and so on. Now, as you all know, the model isn't really the only important thing in what you do. The data is extremely important. When we started this process, we quickly found that the data that's available that people use to train their models is much too small. So it's maybe around 30,000 data points, which is for LLM standards, it's ridiculous. But even for scientific standards where data is a lot smaller, it's still very small. So in molecular, if you just have molecules, not materials, and then they have orders of magnitudes of larger data sets. So what we did is we took data that was already scattered across public databases, and we unified them. So we computed their energies and their lowest energy states with our computational workflows, so that they're all compatible with each other. Because some people, when people publish their results, then everybody uses different settings to compute, let's say, the energy of the materials, so that in the end they're not really compatible with each other. We unified all of them. We have maybe roughly 1 million data points in a reference data set, from which we extract about 600,000 data points, which is about 15 times larger than what people have previously been training on, the MP20 data set. Here we can see just what just some randomly selected outputs look like. They are material scientists in the team. They're happy with this. I'm not a material scientist, so I take their word for it. And this is just a qualitative look at the generated structures. But of course, in the end, what we want to do is we want to have some metrics that tell us how good is the stuff that we're generating. And this is actually one of the most challenging parts of this project, really. Coming up with good metrics for generative models is extremely hard. We did our best. It's probably not perfect, but here's what we did. We want to generate materials that are stable. They should be diverse, and of course novel. It's not useful if we're just generating stuff that's already out there. So novelty is fairly easy to get. Diversity is, I guess, also fairly straightforward. We don't want to just predict the same, it could be a new structure that we're generating, but maybe if 80% of our outputs is just the same structure over and over again, it's also not great, because we want to really scale up the amount of data that we can use to search for relevant materials. So that's something we try to measure, diversity. And we measure that with the percentage of non-duplicate structures. So you generate maybe 1 million structures, and then you just look how many of those are unique and not duplicates of one another. And then stability is, I guess, the hardest to measure, and that's really a proxy of the question, can we make the material? Because that's of course the most important one. If you have a material and maybe your computational workflow tells you it has all the properties you can dream of, but there's no way to make it, then it's not useful. So we try to approximate, and the question of whether you can make it is really impossible to answer with just computational tools. In the end, it has to be a practitioner that tries to make it, but of course we can try to use the best computational tools we have available to approximate the question of whether something is stable, can be made or not. And here this is a bit technical, but we measure how many structures that we generate are within 0.1 electron volts per atom. So this is measures the energy of that structure above what we call the convex hull of the lowest energy structures. And this is, for example, like with diamond, it's not on the hull, it's not the lowest energy structure you can come up with for carbon, but still it's close enough to this hull that you can still make it under certain circumstances. So what we summarize this with the percentage of Sun materials, which are stable, novel, and unique. All right, so with that out of the way, we start from the current state of the art, or the previous state of the art, which is CDVAE, Crystal Diffusion Variation Autoencoder that was trained on MP20, and then we swap in our custom diffusion process and our own model architecture. We see a 1.5 times increase in the percentage of stable, novel, and unique materials. And then the second step is we take our big data set and train a model on that, and that leads to 1.8 times increase in the number of stable, novel, unique materials. So this leads to an almost 3x improvement over the previous state of the art. And then another measure that we looked into that tries to tackle, or that tries to measure what's the quality of the materials that we generate is the root mean square deviation from the relaxed structure. So what does it mean? Our model just comes up with a 3D material. The next thing we do is we throw it into our computational workflow DFT, which is quite expensive, and that first relaxes the structure to its lowest energy state. So it just applies, follows the forces to find the equilibrium structure. And then, of course, you can ask how far away from this equilibrium structure was your initial proposal. And the closer you are to the final equilibrium, we argue the better is the initial proposal, of course. And there we see that just by going from the CDVAE architecture to our MatterGen architecture, we get a 3x improvement, and then going to the big data set gives another 5x improvement. So in the end, we're really, really very close to these equilibrium structures. And then to leave a bit room for question, I'm just going to go through this quite quickly. What I've talked about is, of course, just the unconditional generation, which arguably is not the most useful thing you can do. Really, we want stuff that's close to a certain property we have in mind, maybe also comes from a certain chemistry, has certain atoms in there, atom types in there, maybe has a certain symmetry, which is very important, or has some property like band gap or magnetic density, whatever you come up with. And how we tackle this is we have an unconditional base model that we train on our big data set, and then we fine-tune it to the property data, which is also a lot more scarce than just structures, because properties are very expensive to compute often. And then we have this fine-tuned model that we can then use to generate materials with a certain property prompt, if you will, in mind. So you tell it, give me something with magnetic density 0.2, for example. And the way it works is we use this unconditional score network that we train, and we combine it with the conditional model that we fine-tuned, and that's what we call classifier-free guidance, and that's also what's being used inside DALL-E 2 and Stable Diffusion to guide the images that come out of these models, to guide them to match the prompt that you put in. So you say, give me an image of an astronaut riding a horse, and this classifier-free guidance is really what guides the model to predict structures that match these constraints. So, in an abstract sense, you can think about that way. So you start from this random distribution, and then you're really interested in generating materials from maybe one mode that are stable and satisfy your property constraints. Right. And let's see how that works. So we evaluated these 3 properties in our paper. The first one is the magnetic density. So it's a proxy of how strongly magnetic something is, even though that's just the magnetic density on its own doesn't tell you that. There's more checks you have to do, but it's kind of the first approximation to it that we could find. We looked at band gap, and we looked at bulk modulus, and bulk modulus really tells you how hard something is. So diamond is really off the charts, for example, because it's extremely hard. And with the dashed bar, you can see what's the target property value that we wanted to get, and the dark shaded area, dark shaded histogram is the property values of the stuff that the model outputs. And this is validated with DFT. So and the light, this teal, this greenish area is the data distribution that we train on. So for example, for magnetic density and bulk modulus, you can see that we're really generating stuff that's quite far outside of the bulk of most of all training materials. We also compared to maybe a more traditional approach where you just, again, you have a set of materials, which in our case is these 600,000 or 1 million reference data points, and you use a property predictor that predicts you the bulk modulus, the hardness of a material, and then you just go through your list in descending order. So you start with the one that is predicted to have the highest bulk modulus, you pass it to DFT, the best computational method, you have to estimate it, and then if that satisfies the constraint, then you're happy and you keep it, and then you just keep going down. And this is what we see with this screening curve here. So this is really, we take the top X predicted values from our data set and check whether they fulfill the constraint of having more than 400 bulk modulus. And that initially works really well because there are some structures in the data set that actually are high bulk modulus. But of course, as you go down the list to less and less promising candidates, this kind of flattens out at some point. At some point, there's just nothing more in your data set that you can add that has this property constraint. On the other hand, of course, with our model, you can just keep generating stuff. You can just keep generating thousands and thousands and thousands of materials with that property constraint in mind, and you can really see that after some time, it really overtakes the traditional screening approach and just can come up with more proposals. Right. So this is it. Thank you so much for your attention. I don't want to end before thanking all the many collaborators at Microsoft Research. It's really a very, very collaborative project, and it's really great to have material scientists, computer scientists, physicists, all working jointly to make this happen. And yeah, thank you everyone. Thank you very much.
Thank you, Daniel.